After discussing continuity equation, let's move on to finding the magnetic field for a given current. And the law, so this is like the Coulomb's law in the context of magnetostatics, and this is known as the Biot Savart law. If we have stationary charges, we get constant electric field, and similarly, if we have steady current, that will lead to a constant magnetic field. And for what do we mean by steady current? Steady current means that divergence of the volume current density that goes to 0. And in this kind of a situation, the magnetic field in its vector form as a function of the position vector can be expressed in terms of the current as mu naught over 4 pi integration current cross r cap over r squared dl prime. Now, I will have to explain what it means. Let us consider a current carrying loop like this. Let us consider the current I is flowing in this direction, and we have a point of observation here with position vector r, and here we consider a line element dl prime, and this vector is r vector. In this context, we can write this equation where we have mu naught is known as the permeability of free space. Magnetic permeability of free space. So, the value of mu naught is 4 pi times 10 power minus 7 n per a squared. What is the unit of magnetic field? Unit is Tesla, which is 1 Tesla equals 1 Newton per ampere times meter. Tesla is also written as T. Now, let us see an example of how to calculate the magnetic field using Biot Savart law. Let us consider a current on a straight line like this. This is a wire and it is carrying steady current. This wire is very long, so we will assume it well, the wire is not very long, please delete that part. So this wire is carrying current amount I, and we are interested in finding the magnetic field at a point here, our point of observation marked as P at position vector r, that is at a distance s from this current carrying wire. How do we find that? We want to find B at the position vector r, that means at the point of observation P. So let's consider an element of line, that is element of current here, it's dl prime, and the distance of our point of observation from that line element. Let me try drawing a better line. Is r. This is the vector, and let's say this angle is theta and this angle is alpha. If we have this arrangement, then we can try finding the magnetic field due to any segment of the line. If we consider this segment, and if we consider our point of observation here, this is the perpendicular distance, say this angle is theta 1 and this bigger angle is theta 2. So we can find for any theta 1 and theta 2 the magnetic field due to this current I. Okay, how do we do that? In this diagram, we can see that I cross r cap. So r cap is along this direction and the current is along, r cap is along this direction here, and the current is along this direction here. So I cross r cap, that points out of the screen. Because I cross r cap points out of the screen, that will be the direction of this magnetic field, and the magnitude of the magnetic field would be r cap cross dl prime cross r cap it will, its magnitude is dl prime sine alpha, that equals dl prime cosine of theta. The direction points outside of the screen. Now, if we write L prime as s times tangent of theta, that means this length is L prime, then we can write dl prime as s over cosine square theta d theta. With this expression, we can write, with the geometry, we can write s equals r times cosine of theta, that implies 1 over r squared equals cosine squared theta over s squared. So we have everything that goes into the expression for the magnetic field. Now it's our job to calculate the magnetic field. Let's do that. We have to integrate. The magnitude of B will be given as mu naught I over 4 pi integration if we consider the line segment with that makes angles theta 1 to theta 2. Now, these theta 1, theta 2 could be any arbitrary angle, and you can cover any length of the wire by adjusting these two angles. This will give us cosine squared theta over s squared times s over cosine squared theta times cosine of theta d theta, and that is nothing but mu naught I over 4 pi integration theta 1 to theta 2 cos theta d theta, and this integrates to be mu naught I 4 yeah, so we missed one s earlier. Here we had 1 over s square, here in the numerator we had s. So, in the denominator we will have s, and s comes out of the integral because integration is over theta. We have mu naught I over 4 pi s sine theta 2 minus sine theta 1. This equation gives the magnetic field for any straight wire segment in terms of theta 1 and theta 2. Now, if we consider an infinite segment of a wire, for an infinite segment we will have theta 1 equals minus pi over 2 and theta 2 would be pi over 2. Now, if we put this, then the magnetic field becomes mu naught I over twice pi s, and what is the direction? The direction in this case in our cylindrical coordinate system will be along phi cap, because if we consider this situation here, it will the magnetic field will point out of the screen, and out of the screen is phi cap direction. So, this is the expression of the magnetic field for this kind of a system that we have calculated using Biot Savart law and integrating over the line element through which the current is passing. Now, if we consider two parallel wires that are carrying current, I1 through one wire and I2 through another wire, we have two parallel wires carrying current. This is I1 and this is I2. We are supposed to find the force between these two currents. The magnetic field on the second one due to the first wire, on the second wire due to the first wire, can be given as mu naught I over 2 pi times the distance between these two wires, let us call it d. This is due to the first wire. So, we have I1 here. So, the force on the second wire is I2 times mu naught I1 over twice pi d integration over dl. Now, the total force is obviously infinite. If we have infinite extent of these wires, the force per unit length that can be given as mu naught over twice pi I1 I2 over the distance between these two currents.